All right. Hello, everyone. I hope you are all doing well, and please stay safe in this pandemic situation. So, as you know, we cannot have our lab sessions in person, so that's why I'm creating these videos and posting them on Canvas so you can have access to the Lab 5 material. For this video, I'm gonna talk about the MCDM methods in Python, and in the next video, we're gonna see how we can implement those in Excel as well. So I just downloaded the Python file that I uploaded on Canvas, so you can go and find it there. And basically, we want to see two different approaches here in performing MCDM methods. The first one is the manual calculations, and the second one using a very interesting library that we have as SK criteria or scikit criteria. And this library is really handy, and you will see how easy it is to work with this and how quickly we can get the results out of this library. So let's get started. I'm gonna show you a little bit of background. Let me see. Okay, I can't do that. Let me bring my Adobe here. Okay, guess you can now see this. Okay, the first method that we are looking at is TOPSIS. In TOPSIS, same as other MCDM methods, we have M alternatives and which are evaluated by N attributes. So we can assume that instead of M alternatives, we have M points in an n-dimensional space, right? This is an example here where we have two attributes, attribute 1, attribute 2, and then we have a bunch of alternatives here as a point. So in TOPSIS, the goal is to find alternatives or the points that have the closest distance to the positive ideal and longest distance with negative ideal. So what are these positive and negative ideals? So if you look at one example here, so for example, for this case where we have some applicants as alternatives on each row, and then we have some attributes on each column. For finding the positive ideal, for example, we go and for each column or each attribute, we go and find the maximum value or the best value, the top value. So if the attribute is benefits, is a benefit attribute, then we are looking at the highest value. If it is a cost attribute, we are looking at the smallest value, right? So here, as you can see, all of these attributes are benefits, and so we are going to find the maximum value of each column. So we find the maximum value of each column. For example, here 700 for GPA, the maximum is 4.0, and so on. And then we create that positive ideal using the maximum of each column. For negative ideal, we just select the minimum value of each column and then create the negative ideal. There are some steps for performing the TOPSIS. I quickly explain each of these, and then we will see how we can perform those in Python. The first step is calculating the normalized value. So this is a very common and important steps in all of the MCDM methods. Here in TOPSIS, it is common that we use vector normalization, and by that we means that we divide each attribute by the square root of sum of squares of that attribute. So for example, if you want to find the normalized value for this 690 here, we go and find the square root sum of squares of each of these column, and then find that value and then divide 690 by that value, and then we get the normalized rating, and so on. For each column we will do the same. Next, after we find the normalized values, in the second step, we calculate the weighted normalized values. And for that, we just need to multiply the normalized value by the weighted, the weights that we have, which is specified either by the problem itself, or we have to find it through the methods that we have in the book. Next is identify the positive ideal and negative ideal, same as the method that I mentioned before. And finally, we are going to find or calculate some separation measures. And basically, it calculates the distance of each alternatives from the positive ideal and negative ideal. And using those measures, we can find the similarity. So using the finding the similarity terms, then we can use that to rank the alternatives. So the alternative that has the highest similarity gets the rank number one, and the one with the lowest value of the similarity get the lowest ranking. Okay, so let's see how we can implement that in Python. so I will first show you how we can do it using manual calculations, and then we will use that library. So first we import the required or necessary libraries, pandas and numpy, and then we just need to create our data sets. So as we know from the previous videos on Python, that in order to import the data, we can create our data set in a CSV file and then import that using the pandas library. But here, because we had a very small data set, I just created myself. I just entered the values manually. And these numbers comes from the example that we have for the TOPSIS section in your book. So if you look at this table, so you can see, for example, this is the first row that we have 693.19, 7 and 4, and so on. So this is the data from this table. And the way that we put in the data in using a list is that each list, as you can see, represents one row. So we have the first row in this list, and then we separate the rows with comma, and then the second list, and so on. And then we put all of these lists in one main big list, so which creates the matrix for us. The second item that we want to create is the weight list. So a list that contains the weight for each attribute. So again, we got this from the example in the book, right? These are the weights for each attribute. So for example, the weight for the GRE is 0.3. And sum of all of these is equal to 1, right? And then I also added the names of the applicants all alternatives, so we can have a view of the names in our table or data frame. And here we create our data frame. As you remember, whenever we wanted to deal with tables, matrices, pandas library was the suitable library that we wanted to use. And here again, we use the data frame to create that table shape matrix or data frame that we have. So we go pd for pandas data frame, and then within the parentheses we give in our raw data, this big list, and we also specify the index names. So we have the index name here as well. So let me run this actually different part of this code so we can see what's going on. I'm just running these cells, and if I run this, okay, we get this table. Oh, where is it? Here. So we have the alternatives, we have the attributes. So let's see how we can do the TOPSIS using the manual calculations now. So the step one was the normalization, if you remember, that vector normalization. And so this is the final version of the calculations, but I will show each step of these calculations so you can understand it better. So the first step that I want to do is to find the squared value of all of these attributes, right? So let's do that. Then what's happening here is that, let me create a new cell, And then here I use the numpy power function to find the squared value, and then go data, and this data comes from here, right? We stored that data frame in the data variable, so this data contains all of these attribute values. And then it's going to be power of 2, so I specify that. And then if I run this, you can see that we got the squared of all of these values, right? So the next step is I want the summation of this squared value for each column, right? So because this vector normalization is per each column. Then for that I go dot sum and then I specify the axis that I want to perform the summation toward that. So by this, the 0 represents rows, 1 represents columns, and by specifying 0 here, it means that we want the summation to be through the rows, so it goes for sum these up together for each column. So if I do that, you see that for each column 0, 1, 2, 3, 4, we have the summation of the squared values. So the next step is to find the square root of that summation, right? And for that, again, I use the numpy function square root, the whole thing, and then if I run this, I get the square root values as well. So now we have the values that we wanted to in the denominator, and then we just need to go attributes divided by those values, right? So very easy, we can just put the data at the beginning and then include the division sign, and then if I do that, we get a table that the values here are divided by the square root sum of the squares of each column. So yeah, so as you can see, it's like very similar, like exactly the same as this guy. And then I stored this new normalized, weighted normalized, not weighted, sorry, the normalized values in the data underscore norm. So I just remove this, I just delete this because I have this here, and just let me print it to just have the view of this table. The next step, oops. The next step is the calculate the weighted normalized rating. We just need to multiply the weight by each normalized value. So for that, we just go and we already defined the weight list, right? So we have the weights here. So it's very easy. You just need to multiply this data frame by the weight. So it multiplies the for example, what it does for the first column is that it takes the first column and it takes the first weight and it multiplies them together. And if I run this, you can see that now we have the weighted normalized ratings. Step 3, as you remember here, is to identify positive ideals and negative ideal. So for the positive and negative ideal, one very simple way is to do this. So we already have this table, which is the weighted normalized value, right? For the positive ideal, for example, what we do is for each column, we go and find a maximum. So basically, we want to find the maximum of each column. So for that, we go W and then we use the max method. Then if I run this, it gives me the maximum of each column. You can do the same and find the minimum, and it gives me the minimum. So we can assign those values to positive ideal using max, and negative ideal using mean. And okay, and you can see that there is an example of that as well. This is a negative ideal for us. Step 4 is separation measurement. For that, we just need to find the distance of each alternatives from the positive ideal and their distance from the negative ideal. So we want to find these two values. And as you can see, it's just the alternatives minus positive ideal squared summation for all of the attributes, and then square root. So we can do that as well. We have it here. Just write it down from the beginning so you can see it. So the first step is to just go alternatives minus positive ideal, right? So our alternative is alternatives are stored in this data frame, and we go minus a positive ideal. Did I define this? Let's see. Okay, let me see now. Positive. That's ideal. And then after that, we want to have the squared value, and then summation, and then square root. Okay, so for the squared value, we use numpy power, and it's a power of 2, and then we use sum, and this times the axis is 1 because we want to have the summation for each row this time. So it's not this way, just this way. And then we go numpy sqrt for the square root, and that's it. So this is basically the distance of each alternative. For example, for Alfred, the distance of Alfred from the positive ideal is this, and so on. And we can do the same for the negative, and find the distance from the negative ideal. So now we are looking for the alternatives that has the lowest values of these negative ones and the highest values of the positive one. So I stored these two values in SMP and SMN for positive and negative, and this is the separation measurement. And the last step is to find this similarity term, and just the negative divided by positive plus negative. So that's exactly what we have here. And if I run that, we haven't run this. Okay, run this, and then if I run this, we have now this similarity measure. Now we can rank them based on these values. So the ones has the highest would be the best option for us here. Is this guy has the highest value, so this is our top choice, and we can rank them based on these numbers. So this is, I believe this is exactly what we have in this example as well. Yeah, these values here, if you look at those, just exactly same as what we got here. So this is the manual approach for doing the TOPSIS in Python. It's not very complicated, but it might take some times for you to do that. So it might not be the most efficient way to perform TOPSIS, especially if you have time limitations. For example, if it's on your exam. That's why I would recommend using this library instead, if the approach is available. So this scikit criteria is a very useful library. So there is a documentation for that. It's really straightforward. I have posted this on Canvas, so you have access to this. So whatever method you want to use, you can just simply search for it. So for example here, TOPSIS, and you can see some examples of the implementation of TOPSIS. So I can also search ELECTRE. You can see ELECTRE and weighted sum method, yeah, and so on. So it has the some of the most famous approaches, but it doesn't have all of them. So for some of the approaches, you might still need to do the manual calculations or find some other libraries that has this kind of methods. I found SciFi very useful in finding uh, those kind of methods as well. But this is very straightforward. The first thing you want to do is to just install this library on your environment. Using this line of code, actually you can install that. If I run this, because I've already uh, installed it in my environment, I get this message, but you will get something else. You see the installation process. But after this step is finished and you have this library installed on your environment, you can use that. And then what we want to do is to import some modules and functions from this library. So from escape criteria, we're going to import data, mean, and max, and I will explain the functionality of each of these terms. So let's run that, and then what we want to do is to I define the names of the attributes as well here. We could do that in the previous step, but I just did it here. It's the names of the attributes basically. And then this is a new part here that we want to also define this criteria variable, and basically this is a list, and within this it will be filled with max and mean, the items that we have here. And each of these is corresponded to one of our attributes. So this one is the first attribute, the second one, and so on. And basically it tells the code that whether we want to maximize that attribute or not. So if we want to maximize that attribute, or if that attribute is a benefit attribute, we use max, and if that's a cost attribute, we use mean. So for this case, all of the attributes are benefits, so we just want to use max for all of them. Okay, so we created the criteria. The next thing we do is the step that I really like from this library, is that it gives us the opportunity to create a table that includes all the information needed to do a MCDM. So basically, for performing MCDM method, we want to have the raw data, the numbers. We want to have the weights. We want to specify whether the attributes are benefit or cost. And that's it. These are the three main items that really want to do. We want to deal with in these kind of methods. It also has some other parameters as well that I will go through as well, but these the three items that I mentioned was the three mandatory ones, the one that are really necessary to be included. So the first one, so we are using this data function that we imported here, right? The first one is the matrix or the input data that we had in the previous step. So remember from the previous step, we already have the matrix and weights, right? So we didn't redefine those here, so we just use them. The second parameter is the criteria that we defined here. The third is weights, and we also can include the alternative names and criteria names. So it's not necessary, but just to make the table look well, we can to look better, we can add these as well. So this comes from the previous step that we defined the names of the alternative names, and this guy is the one that we defined here. The weights comes from the W list criteria is here, and the matrix is from the previous part. So if we run this, now we have, so we didn't run this part. Okay, if I run this, okay, we didn't do this as well. So let me run all of these. Okay, and now print our data. So we get this table. So this is really interesting. So we have the alternative names, we have the attribute names, we have our numbers or values, we have the weights in that table, and we know that the attribute is benefit or cost. So it's a very complete table that includes all the information we need. So if you have one tip here in completing this part, is that if you have some issue, uh, if you don't remember which one should comes first, second, and what were these parameters, so you can do this instead. I can create a new cell here. So you go data, and then you add the parentheses, and when you are between these parentheses, if you hold shift and press tab, it gives you some kind of instruction for filling out these parameters. So it tells you the first one is the matrix or the data, the second one is criteria, mean and max, the third one would be the weights, the fourth one would be the A names, which is the alternative names, and so on. We have the criteria names as well. So you can use that as well. But anyway, so if we move forward, so another interesting functionality of this data frame is that we can plot uh, the values that we have and see have a visualization of our data set. So here it's what happened basically when we plotted a box plot of different attributes that we have. So the way to do that is that these two parts are just importing the matplotlib library. Remember that whenever we wanted to visualize or plot a graph, we had to import the matplotlib library. And then this part is the magic function only for the Jupyter. So these two just a regular or common uh, codes that we had from the previous uh, labs as well, but this is the part that we want to focus on. So we have our data, which is this table, and then we go plot, and then within the parentheses we specify the kind of the plot that we want to basically plot. We the box, I plotted the box plot, but we also have other options as well, so you can try these as well. And uh, I also add the normalization step here. So I wanted to normalize data to be plotted, because if I remove this part, you will see what happens. Because the GRE values are quite big, that there is no space, so like these uh, other attributes becomes really flat, and you can see the distribution here. So that's why we are using that normalization term here. So this is the normalization term, and then we specify what type of normalization we want to perform. So we can, in this library, we have the vector normalization, and we also have the sum normalization as well. It doesn't really change our, well, it changes a lot, yeah, at least the y-axis it changes. But yeah, but for the TOPSIS, the vector normalization is the common type of normalization that we use. Anyway, so we have created this one, and as soon as we create this table, then the rest of the code would be really easy. Just we need 2 lines of codes to perform the MCDM method. So let's see how it works. So this is the whole thing that we want to do for performing a TOPSIS. So the first thing is to import the TOPSIS. So we go scikit criteria, multi-attribute decision making, and from closeness module we can import the TOPSIS, and then we define our decision making tool, which is TOPSIS, and then within the parentheses we specify the normalization method, which is vector normalization, and then we use the decide function using our decision making tool. We go decision making dot decide, and then within the parentheses we give in our data that we want to be processed. And when we do that, we will receive a very nice table. We have that table that we had. We also have an additional column, rank, which uh, gives us the ranking of the alternatives based on that method that we specified. Uh, so it is really nice library, and I really recommend using this library if you're working with Python. Um, with has the TOPSIS, we can also use the weighted sum and weighted product methods. These are the methods in chapter 4 of your textbook, and basically they are in the simple module in multi-attribute decision making. Uh, the steps are exactly the same. As soon as we have the data created, we just need to change the method. So the difference between this part and this part, the TOPSIS part, is just the name of the method. So for example, here we use the weighted sum, and instead of vector normalization, we used sum normalization, which is more common to be used in weighted sum method. And then decide function, and the data is exactly the same. So if we run this, we get the ranking based on this method, the weighted sum method. Weighted product method is exactly the same. And one thing I just wanted to add here is that the decide function gives you a very nice table and the ranking as well. But if you really want to have the scores and more detail about your method, instead of decide, you can use the solve function, as you can see here. So if we use solve function, so this is, for example, this is a decision making tool for the weighted product method, the ones that we had here. So what it gives you is that a list of the ranking, so it's exactly this column. Also the scores which the method used to rank these alternatives. So if you want to have more details of the method, I would suggest to use the solve function instead of decide function. I mean, it doesn't hurt if you run both of these. So you also have both the table and the details next to each other. Again, all of this information and examples can be found in this tutorial instruction that I will post it on Canvas. I really recommend that go through these examples and see. You can see the different plots and different functionalities of this library. It is really helpful and straightforward. Okay. The last item is ELECTRE, and let me quickly explain how this method works. So it's going to be your chapter 6, and the goal here, I mean, I would really suggest that you read through read your textbook on this chapter and see how it works. But basically what it does is that it finds the top choices for you. It doesn't rank them, but it just excludes the ones that are not the top choices for you. So what it does basically, it creates a kernel for you, this K, and it puts in the top alternatives in it. So basically it reduces the number of choices for you. So one good implementation of ELECTRE method is that to use ELECTRE in order to decrease the number of alternatives, and then after that use that new set of alternative in another DC MD method, for example, another TOPSIS. So you first run ELECTRE, you find the top 3, top 4, and then use top 4 in TOPSIS to find the top choice or rank them from 1 to 4. There are some cases that when we have, for example, when we have a small number of alternatives, for example, 3, it might gives us only one attribute in this kernel. In that case, we know that our top choice is that specific alternatives, and really don't need to do another decision making method on top of that. But if this is a special case, it doesn't happen all the time. So whenever we got more than one alternatives in our kernel, then we need to perform another decision-making, multi-criteria decision-making method to find or rank our alternatives. But anyway, in order to perform the ELECTRE, we have to define two parameters, concordance and discordance. And basically, for concordance, what it is that it measures, it tells for the attributes, for example, uh, for I would say, let me put it this way. So for each attribute, for each set of two alternatives, it tells us each alternative is better than the other in which attribute. So for example, this is one example here. So it's telling us, for example, uh, alternative 1 is better than alternative 2 in attributes 2. And for this one, for example, alternative 2 is better than alternative 1 is in attributes 1 and 3. And we also have discordance, which is the complement of C. And it contains all attributes for which AP, or alternative 1, is worse than alternative U. So instead of better, we just changed it worse. So for example, here, so we are saying that alternative 1 is better than alternative 2 in attribute 2, but alternative 1 is worse than alternative 2 in attributes 1 and 3. So it's just a complement of the concordance. So once we get these concordance and discordance value, then we have to find the indexes. Index of concordance and discordance, and for that we just use the weights value. What we have here, we have two equations for concordance and discordance, so you can use that and calculate all of these. And then when we found this, then we compared each of these values against a threshold. That threshold can be specified by the decision maker, but one simple way to find that threshold is to find the average. So we take the average of C as the threshold for C, and the average of D for the threshold for D. So what's exactly happened here? And then we create this comparison table. So we want to see, for example, C12 is bigger than the threshold or not. So here is yes, and for D, we want to see if D12 is less than the threshold, yes. If both of them are yes, then AP, or here we have 1 as AP and 2 as AQ, it means that 1 is better than 2. And for example here, for this case, what we have is no, no, and no. So it means that we can say that 2 is bigger than 1. So using this, we finally, and then by comparing this yes and no's, we can create this diagram that we had in the beginning of this chapter. And then using that and the rules that we have for creating the kernel, we can find alternatives that fall into this kernel. So let's see. So for the ELECTRE again, what we need to do is just create our data set and that data table. And as soon as we created that, then it is really easy. This is just very similar to what we had in the TOPSIS weighted sum method and weighted product method. So for this example, for ELECTRE, I used the example in the book for the ELECTRE chapter. So this is our data set. We have 3 rows. Each row has 4 columns, 3 columns, sorry. And then we specify the criteria for ELECTRE. The first one is mean and max and you also can see this in this example here. So it tells us that attributes x2 and x3 are benefit criteria, and then attribute x1 is cost. So we just want to minimize x1, maximize x2 and x3. So that's why we put in that mean here. So the weights are also specified in the question in the book. And using this information, we can create that data table, right? So we give in the data, we give in the criteria and the weights. So if I run this, and then I also can print the okay. Oh, why it's not? That's a mistake. Okay. So yeah, we have 3 alternatives, 3 attributes, and these are the values that we have. So for the ELECTRE, we go and from the ELECTRE module, we import the ELECTRE1. So for the ELECTRE, we have different types. So in Wikipedia, for example, you can go and see we have different methods for ELECTRE. ELECTRE1 is the most famous one, but we have different versions of ELECTRE. So in this library, we only have ELECTRE1. So we import that, and then we specify the normalization method, and also we have this P and Q. So these two refer to what we have as the average value here. So if you remember, we have to somehow specify that threshold. So for this example, we use the average, but this is not the only values that we can use. So if you read this part, it also gives some notes about that. But anyway, so the default values for this threshold in this library is 0.65 and 0.35, but we can change this. I just changed it to what we had in the textbook. The average value is 0.5 for both of them. But if you don't specify those, then they will get the default values of 0.65 and 0.35. But anyway, so we do that, and then the next step would be similar to what we had before. We use decide function, and then we give in the ELECTRE data, and then we print out the results. Okay, so it gives us the item that fall into the kernel. So it tells us that alternative 1 or the first alternative, which is A0 here, exists in that kernel. So because we only have one item in the kernel, so we know that this is going to be our top choice. But if we had more than 2, then we had to perform some other methods to specify which one of these is the best alternative for us. This is exactly what we got from the textbook as well. So only alternative A remains in the kernel, so which makes A1 the optimal choice. So yeah, I guess we are done with the Python part. So I really recommend that you guys go and read through this documentation. It's pretty straightforward. And let me know if you have any questions. You can just email me and we can discuss the Python code together. And yeah, thank you so much.